Now, in our 7th video on integration, we have learned the method of completion of squares. Now, let us see how exactly we are going to use this method for integrating functions. Like suppose we have a question of this type, 1 divided by 2x squared plus 3x plus 4, its integration with respect to the variable x, indefinite integration with respect to the variable x. Now, as we have discussed in the last video, that this 2x squared plus 3x plus 4 can be written in this particular format. So I'll do that for you. So in the denominator, I can pick 2 as common. So what I get is 2 here in the denominator outside the integration sign. And within the bracket, I'll be writing x plus 3 by 4 whole square plus root 23 by 4 whole square dx. So with the help of this method of completion of squares, what we have done, what we have achieved is to express this quadratic expression present in the denominator where x was visible at two different places. We converted it to an expression where x is visible at one place only. What is the advantage? Advantage is that we have a formula 1 upon x square plus a square dx. We have the formula for integration of 1 upon x square plus a square dx, which is simply 1 upon a tan inverse of x upon a plus c. So in place of x, I'll be writing x plus 3 by 4, and in place of a, I'll be writing root 23 divided by 4, and my result is ready. So this 1 upon 2 remains outside as it is. Now 1 upon x square plus a square is 1 upon a. In place of a, we have root 23 by 4. So we write 1 upon a. A means root 23 divided by 4 tan inverse x. In place of x, we have to write x plus 3 by 4, and in place of a, just need to write root 23 divided by 4, and of course c, the constant of integration to be written. Now we can justify the constants. We have 2 2s are 4, and we can take this to the numerator. We get 2 divided by root 23 tan inverse. We can go for simplification at this level. For the numerator, the LCM comes out as 4. So what we get here is 4x plus of 3 and divided by 4. And for the denominator, we already have root 23 and divided by 4 and plus of c. This 4 and this 4 can be cancelled out, and we can write 2 by root 23 multiplied by tan inverse 4x plus 3 upon square root of 23 plus c as our final answer. So you have seen how important this method of completion of square is for integration of this type, where we have numerator as a constant and denominator has a quadratic expression where we have the terms of x square and x, both are available. We have x square and we have the term of x also available. If there is no term of say single power of x, then you can on minor simplification go for the direct formula. But if we have the terms of x square and x both visible in the denominator, then for sure you must know this method. Otherwise, integration will not be possible for you to do. Now, what exactly is to be done? I'll just revise it for you once again. Very first thing is to convert the coefficient of x squared to unity. That is done by dragging this 2 outside. Now, once you write this 2 outside, the remaining terms get divided by the same 2. So what we get is x square here, then 3 by 2 of x, then plus of 2. After that, we pick the coefficient of x, which comes out as 3 by 2. We take its half, it becomes 3 by 4. Then square makes it 9 by 16. So we preferred added and subtracted 9 by 16. and then after that we club the terms containing x square and x and the term 9 by 16 we added. On simplification, we arrive at this 2 outside, x plus 3 by 4 whole square plus root 23 by 4 whole square, for which a standard formula 1 upon x square plus a square is available. It is 1 upon a tan inverse x upon a plus of c. So in place of x we write x plus 3 by 4 whole square, and for this we have a square. In place of a we just need to write root 23 by 4. So this is how we can find the integral. We can solve this integral with the help of the method of completion of square. If we have the knowledge, we'll be able to do it with the means complete easiness. But if you don't know this method, then you may be stuck somewhere. So better is to try a few more sums of this type and apply method of completion of squares first, and then you'll be able to do sums of minimum of, you can say, 4 to 5 formats. Like the first one we have covered here is we have a quadratic expression in the denominator, and some more formats will be like square root of this quadratic expression. Another format can be square root of the same expression but inside the under the root, and the same thing is appearing in the numerator. So we have minimum 4 to 5 formats. We do have format where we have linear by quadratic. There also this method is applicable. We need to apply method of completion of square there also, and we need to have, say, something like linear upon quadratic also. There also we can apply this method. But initially let us see the main 3 formats where we have 1 upon quadratic, 1 upon root quadratic, and under root of quadratic. 3 formats where this method is directly applicable. Thank you.